Okay, so what we're going to get into here today is taking a variable speed drive and setting it up on a motor. Straightforward. Stop start button, on off switch, and a potentiometer for speed. It's the basics. This is a beginner's class for how to set up a variable speed drive. Okay, these things are not scary, they're not monsters. You just got to take your time, read the manual, just read the destructifications, spend some time with it, and don't be lazy, be careful, and it's straightforward. These things can do a lot, but you're only going to be using a portion of it. In other words, it gets simple. So it's not powered up yet. Let's go through the wiring quickly. Over here I've got mains connected to it, to the mains input. This is single phase in and 3 phase out. Okay, 220 volts in, 220 volts out, 3 phase. Okay, it does not become a higher voltage. There's no transformer inside here. Connected to it we have got a potentiometer. Okay, just a single potentiometer, and we have a switch. So look at the drawing. So we're going to use analog frequency 1 over here. Alright, so that means we connected to pin 1, which is 0 volts. Pin 2 is the wiper going to pin the analog input. Okay, we need 10 volts on the pot, we need to power it. It's a potential divider. So 4 is 10 volts out from the drive to the potentiometer. Now the current is limited to 5 milliamps. So try and stick to something like a 10k pot or a 20k pot or something like that. If you go down to a 1k pot, you're going to pull down the 10 volt supply and you're going to have problems with your reference. Okay, the switch, I've got that connected to terminal 12, which is your run forward input. Now this drive requires an enable input, but that's a programmable input. Now because on this drive the customer had an oopsie, they got water into the panel and they introduced mains to the control wiring. Terminal 11 doesn't work anymore. But in the software you can invert that bit. So that bit is inverted by an onboard PLC program which I've loaded onto this. So we don't need the enable input, enable or disable input. It can be normally open or normally closed. So basically we've just got a start switch. The potential free contact is over here. That is by default drive OK. So when the drive is in a healthy state or a ready state, that contact is closed. We're not using any of the other inputs. There's a second analog input. There's an analog output, terminal 7, which is 0 to 10 volts out in proportion to the speed. Where did I put my screwdriver? Let's make sure if I do need to twiddle some screws. Oh, here we go. Bump the camera. Then I've got it handy. Right. So that's the wiring. It's straightforward. If you're going to be running this off a supply with earth leakage protection, you need to disconnect the EMC filter. So that's a torque screw down there that you simply undo, and you're not going to trip the earth leakage. Over here is the earthing bracket where you connect your earth your drive over here. So let's get it powered up and look at the parameters. So we find our plug and jam it in the socket, and the drive powers up and it says ready. Now normally it would say INH inhibit without that terminal 11 signal, but I've flipped the bit in the parameters, so it's saying ready. So because we were previously using this, I'm going to default the settings. So I'm going to go to parameter 0, which is where you do stuff like that, and I'm going to select default 50 Hz settings. Now I'm going to hit the red button. So now I've restored it to factory settings. That happens in parameter 0. Let's move that away. Okay, now you can do some electrical checks because we powered up. So what I'm going to do is take my multimeter and let's check that the potentiometer is working. So you go on pin 1, which is your 0 volts, and 2, well, let's go on 4 and check that we've got 10 volts. Yes, we do. Let's go on to pin 2 and see what our potentiometer is doing. Because I was previously working with this thing, it's already turned up slightly. Yeah, the potentiometer is working. Okay, I don't think we've got any lights reflecting off the screen, so you should be able to see that. Good, potentiometer is working. And we can verify that by going into the parameters, because you have on this drive read write parameters, and then you've got the read only parameters, which are status parameters, and instead of an RW you've got RO, which means read only. And if you want to see the analog input 1 value, you go to parameter 94. Now these parameters simply loop around. Now to get to all of these parameters, I need to change parameter 10 to all. Okay. Right, now to get to 0, you hold down the up and down arrows together, and now we're at 95. We want 94. Hit enter. That's our analog 1 input value as a percentage. So we want to see 0 to 100% there. Good. So the potentiometer is working. Okay, next we want to concern ourselves with the motor. One needs to set the drive up to suit the motor. Now this motor, I think I have wired in delta for 220 volt operation. So we need the rated frequency, it's 50 Hz. There isn't a parameter for kilowatts on the drive, because you're going to be telling it what the motor rated voltage is, what the motor rated current is, and from that it works things out. Speed 1310, so that's full load speed, so that is 1500 RPM minus your slip. This is a small motor, so there's quite a bit of slip. Current 1.03 amps and power factor 0.73. And your power factor. Efficiency, if I'm not mistaken, it says 60%. Small motors are not efficient. The resistances in them are high. Okay, so let's start off. Let's go out of here. Now, also on this drive, on the front cover, you got your 10 basic parameters. So you got minimum speed, maximum speed, XOT time in seconds per 100 Hz, decel rate in seconds per 100 Hz, drive configuration. Do you want to run it in keypad mode or from a digital input? Motor rated amps, RPM, voltage, power factor, and then parameter access where we've been already. Good. And by the way, on the back, in case you get lost, there's your terminal descriptions as well. So with it powered up, we should have continuity on that relay, which we do. Good. So let's tell it about the motor. Let's start off with that. So I'm getting our piece of paper. Motor rated current 1.03 amps. So take that down to 3, move the cursor. Move the cursor. Enter. Now parameters, menu 0 auto saves on this drive. When you go into the advanced menus, you have to do a manual save, and there are parameters that only take effect after a save. But for what we're doing here, we don't need to save it. Auto saves menu 0 parameters. Right, so the motor rated current is set. Motor rated speed, we said was 1310, so I'm going to do that. Like so. Motor rated voltage is 220. Let's do that. Now I'm going to do an auto tune, and it's going to spin the motor and work the power factor out itself. Now you can enter that manually or do an auto tune. The auto tune will do two things. It's going to calculate, it's going to measure the stator resistance, the inductance, as well as the reactance of the machine, and it's going to spin it at the same time, and from that it's going to derive the power factor. So to do that, you need to go back to parameter 5 and just see what that's set up for. Now by default, this thing is set up to run off the pot and the switch, which means you don't need to do anything. So now we want to do that auto tune. That's parameter 38 auto tune. We want to do 2, which is a spinning auto tune. 1 is a stationary auto tune, which only does the measurement of the inductance and resistance and calculates current loop gains from that. So let's go to 38 and tell it to do that auto tune. So I'm going to select 2 and escape out the menus. It says ready. Now I'm going to close the switch, and now it says tuning, and you should see that happening. It's running it at 2/3 of rated frequency at this stage. You can hear it getting quieter there towards the end. So that's done the auto tune now. So let's see what power factor it measured. 0.69. Yep, that's very close. So as you can see now, it says inhibit. It goes into a safe state after the auto tune. So what I'm going to do is I'm going to use the soft disable, which is in menu 6, which is your drive sequencer, to just cycle the soft enable bit, like so, and it's gone back to ready state. So now when I give it a run, it goes into a run. Now the escape button toggles between frequency and percentage load. So now when I turn this up, there goes our frequency, and there's percentage load. Okay, now depending on your application, go back to menu 0, minimum reference is 0. Pumps and fans, you'll generally have that at about 30 Hertz, because between 30 and your maximum speed that you want to achieve is generally where the fan or the pump operates. Below that nothing happens. Even refrigeration compressors, you don't run them below 30 Hertz because nothing happens. You're only controlling in that region. Maximum frequency is 50 Hertz. The VST, you can set that faster and run super synchronous, or that will be set to suit the application. If you're running this off an auto 10 volt signal from a PLC and you want a certain maximum speed at 10 volts, you would set that frequency to be that speed. Now over here, that's your axle time. Now over here, it tells you yeah, it's in seconds per maximum frequency. So if I were to set this to 100 Hertz, it would take 5 seconds to get to 100 Hertz. At the moment it's set to 50 Hertz, so it's 5 seconds to 50 Hertz. So these times are your maximum frequency dependent. On the older products it was in seconds per 100 Hertz, but now it's related to parameter 2, which is your maximum frequency. Default is 5 seconds. Decel is 10 seconds to maximum frequency. Now, one of the reasons we entered the motor speed, and it's important to do it, is for the low speed operation, for what's called the slip compensation. So what you want, this motor has obviously not got much torque, but as you load this at low speeds, you don't want it to slow down. As you can see, it's not doing it till I grip it very tightly. So it's got good torque at low speeds. And that's particularly important for loads that need a lot of starting torque, or hoists, which require good control around 0 speed. So that's performing very nicely. The low speed performance is excellent. Now if I were to go in here, the cursor, set those very short, there you can see the things. The time has become very short for the axle and decel, so it's pretty dynamic now. So if you were doing motion with this, that's the sort of response that you'd want out of the amplifier. Even if I were to do this, pretty dynamic. Now this would normally have a fan on the back, and that fan would provide cooling for the motor. Now if you're going to be running this motor for extended periods below 30 Hertz, you would need a separate electric fan on the back called forced cooling for the cooling, because that fan on the back here, once again at low speeds, is not going to provide adequate airflow over these fins to keep this motor cool. And if you examine the current going through this motor at this stage, you can see it's 0.5 amp. That's your magnetizing current, and that is the current that flows, because you need magnetism in here to magnetize a squirrel cage rotor. You see there, as I grab it, that stays constant. There's what's called the torque producing current. When I grab the shaft, that goes up. Now in the case of such a small motor like this, where the efficiencies and losses are kind of big, you really get a lot of feedback from these parameters. You only see a very small change there on the torque producing current when I grab the shaft, but normally that would be a big change. That's quite an accurate indication of the load on the motor, which is why on small motors like these, doing torque control becomes difficult, because you haven't got good control over that. You can do torque control with this. This can also do PID and all sorts of other stuff. But on small winders and stuff like that, where you want to do tension control and have control of the torque, it's tricky to get good control with a small motor like this, because the torque reference doesn't give you good variation in the torque response on the shaft. Tends to be a little bit kind of all or nothing. But anyhow, it's working. So let's see if there's any errors stored in this. Yes, there will be, because I had it connected to a blender over current OI.AC. So the last couple of last 10 errors are stored. That was a PLC program error, also caused by me. Overload digital input 1. I think that was caused by the original owner of this drive when they did damage to it, and there's none. So those are all your stored errors. If you want to see what the DC bus voltage is, 300 volts, so that's 220 times the square root of 2. So that once again is a read-only parameter. You can see it just flashes, so it's showing voltage. So when I start it, you actually see that come down a little bit. This does have a connection for a power dump or dynamic braking resistor. It's got a positive and a negative, a positive and a brake chopper connection over here. There's no negative connection on this. From a size 2 onwards, there is a negative terminal as well. This is a size 1. From a size 2, you can also fit option modules, which is extra I/O, Ethernet, Profinet, Profibus, and that sort of stuff. A couple of options that fit in here. Gives you more digital I/O, some extra relay and stuff like that. Now you can set this up for 4 to 20 milliamp operation as well on the input. If you're using it with the PLC, we're not covering that today. The 24 volt out of this thing is on terminal 9. So these inputs, to turn them on, you want 24 volts on them. So if you're trying to troubleshoot your digital signals, go on to pin 1, see your 0 volts, start off with checking for 24 volts, and then check your digital signal. There you go, 24 volts, and your motor runs. Okay, so there are two things to get this VSD going. You need your reference over here. So there's your reference. Now you need a run signal, and there's your run signal. Motor spins. Okay, those are the two things you need, and the motor will turn. Okay, if you have configured it to use those inputs for speed and start, you've done it right. It will run. If you're using it on a PLC, where the PLC supplies a 24 volt signal to start it, your 0 volts needs to be common to the PLC, obviously. And the PLC, I'm going to send 24 volts here, and it's going to start it. Okay, and I can demonstrate that. I happen to have something like a PLC over here. Let's turn it up to 24 volts. It's called a power supply. So I'm going to put its 0 volts onto that probe. I'm going to put my other probe onto the digital input, and I'm going to give that digital input 24 volts. Voila! Your motor runs. That's simulating a PLC signal, just like that. Okay, so if you're working with PLCs, remember about the 0 volt common. Remember to turn that power supply down as well. Now this thing has got a digital output, terminal 10, 0 speed indication. And just turn that screw all the way in, because the screws, until they're seated, generally don't have contact with the contact. Sounds funny, but yeah, there you go. So when I start it, that goes low. So that's motor stationary indication, like that. Then we said we had an analog output. Let's also turn that screw in. We covered the basics, but we're getting into a little bit more advanced stuff here, but that's okay. Here's your analog output. So you can see there's our reference, there's our analog output. So that's motor speed. So let me show you something here. Now let's set that. Fairly long time. Same with that one. And remember that you can move the cursor like this. You don't have to scroll all the way through, okay, because that takes forever. Okay, now as we know, as I do that, that voltage on the pot comes up quickly. Watch what's happening to analog output. Because I made the axle time long, that's indicating actual motor speed. So now whack the pot up to 10, There you see the feedback speed coming up like that. Similarly, when I give it a stop, it's showing motor RPM. That often goes to an instrument like a meter or back to a PLC to indicate speed back to a process program. So there you can see it gracefully coming to a stop, just like that. I'll set the time fairly long. This is process dependent usually. And there we have it. This thing can also be used to work hoists. Cranes. So it's got an output for the brake. Relay. I heard the relay click. So currently that relay is closed because that relay is going to control the holding brake on the crane. So when I close the switch, you see that coming to a standstill, and you see that relay open as it closes the brake again. Now here, notice that the motor starts spinning a little bit before the relay opens. Let me set it to buzzer. I don't think the buzzer works on this meter. I think, yes it does. Did you notice that the shaft turns before the beeper comes on? That's because it produces torque against the load before releasing the brake. That is in order to provide torque and also to provide magnetization in the rotor, so that when the brake releases you've got control over the motor. And there's a delay in it, so it runs at a slow fixed speed and then speeds up once the brake is released, like that. Anyhow, that's brake control. As I say, there are many things you can do with these VSDs, but we've covered the basics today. You can take one of these VSDs and you can set it up, you can make it go. These things all work the same. You can take a drive from any manufacturer. Some of them, the books are harder to read. You're going to find that this is the same. Analog signals, digital signals. That's it. Drives all work the same. When it comes to this stuff over here, some manufacturers are not so easy. This is a particularly easy product, but some of them it's sort of not as self-explanatory, and it takes more time to work things out, or things are grouped differently, and it's confusing, especially if you're used to one brand and now they do things and you suddenly have to work on another brand. I've worked on many of them. I've worked on Allen Bradley, ABB, Danfoss, the Rockwell stuff, Siemens, worked on Schneider, worked on SSD, worked on Parker, I spent all my life working on these Control Techniques drives. Spend your time with it and you can figure it out. And don't get caught up in everything that's in there. If you just want to turn a motor, just use those basic functions to turn the motor and you're good. And the general precautions in working with live stuff apply. Be sensible, and wiring hygiene, running analog signals away from main stuff, and your proper earthing and all that sort of stuff. Do it right, do it neatly. The guidelines for doing it are in the manual as well, and you can also Google it if you don't know how to do that sort of stuff. There's lots of it on the internet. So we've set up a drive. That's it. It was that easy. Okay. I hope this video was helpful to lots of you, because I know so many people battle with variable speed drives and so many people are scared of variable speed drives. Really, it isn't. They are not monsters. They are not something that only clever people can work with, only certain people can work with, or you have to have special training or go on courses and so on. No, anybody can work with these things, okay? It was as easy as you saw me do it today. Alright? Please. So I hope you can take away something from this video. Hope you enjoyed it, okay? And I hope many people watch this video and benefit from it. Alright? So this video has been going on for a while now. It's time to wrap it up. Thanks for being here, ladies and gentlemen. Thanks for watching the video all the way to the end if you're still listening, and I hope you are. And I hope you liked the video. Take care. I'll see you next time for more stuff with electronics or stories, because I have an interesting story to tell about the first time I was commissioning a big drive on a induced draft fan at the cement factory on the kiln, and it went kapooey. And it built character that day. So we'll get to talk about that, so keep an eye out for that video. So till next time, cheers.